Welcome to Lecture 7. In the notes, it's right here in the notes, it's identified as Lectures 7 and 8. So let me tell you what we're going to do in Lecture 7 and how far we're going to get into ionic bonding. We are definitely going to cover periodic trends, as shown here in the overview. We are going to begin bonding in general, talk about the different types of bonding, and start ionic bonding. Lecture 8 will pick up and finish ionic bonding. All right, so we are going to start off with the important trends. Here is another one of those referenced videos from another source that you might want to look at if you're interested in learning a little bit more about the development of the periodic table. The periodic table was developed by Mendeleev and another person whose name I am forgetting at the moment. Ivan somebody. Anyway, in the mid-1800s. And Mendeleev was able to essentially come up with the arrangement that we all, pretty much almost the arrangement we use now, based on what he could see. Mid-1800s, Dalton's model was pretty much the prevalent model, which, considered atoms as BBs. There were no subatomic particles known at that time. So he was able to arrange those elements in their groups, their families, which we now know have the same number of valence electrons, based on their similarities in chemical reactivity. He even created gaps where elements had not been discovered yet. There are quite a few that had not been discovered, based on putting elements into rows and columns based on their similarities. So we're going to get started with the most important trend, and that is that of atomic size. So if you look at this little, like this little table here, because it shows it to you, with a picture. I am a visual learner, and it shows how atomic size changes as you go down groups and across groups. So we need to talk about trends. The convention is to talk about what happens as I go across in this direction, and we're going to talk about 3 trends, and what is happening as I go down groups, just to be consistent so you don't get confused about learning it in some other orientation. This is the most important trend because the other 2 that we're going to talk about rely on this one. And they're opposite of this one. So if you memorize this one, you'll know the other 2 because they're opposite. All right, this one is really important because this one is going to govern pretty much everything else. Size is important. All right, so we see, first of all, that the largest atoms are down here in the lower left-hand corner. And the smallest atoms are up here in the upper right-hand corner. All right, if you want to memorize it in that way, you can. That would be a good way to do it. However, if we're looking at a row on the periodic table, I am seeing that atoms are getting smaller. Now let's review what we know about the periodic table in terms of shells of electrons. If I am on the first row of the periodic table, I have 1 shell. If I am on the second row of the periodic table, I have 2, and so on. So what elements have in common in rows is the same number of shells. So that's layers, like layers on an onion, same number of shells. That's what those elements have in common. Electron configurations are changing as you go across. If you come down here to the n equals 4 row, you start off in the s block, then you're in the d block, and then you end up in the p block. But you see that atomic size pretty much is a clear trend of decreasing as we go across. They have the same number of layers. So why are they decreasing? Well, the answer to that comes in the nucleus. If we think about the nucleus, remember, tiny little living space, this is where all of the protons are located. Well, protons attract electrons. One of the prevalent attractions in chemistry is one atom's protons attracting its own electrons, and that's what's going on here. When we start to talk about bonding, it is one nucleus attracting not only its own electrons, but the electrons in a neighboring atom. But anyway, we digress. So as we're going across, you've got the same number of layers, but what's happening in the nucleus is the periodic table is arranged by increasing atomic number. So as we go across, that's what's changing. What's changing is the number of protons in the nucleus acting on the same number of layers of electrons, or pulling on the same number of layers. So if I talk about the third row of the periodic table, which is this one right here, do a little erasing. Okay, so let's, big eraser. So if I'm talking about the third row of the periodic table, it starts with sodium, which has 11 protons in its nucleus. All right. Once I get over here to the end with argon, argon has 18 electrons in its nucleus. Well, here's 11 protons pulling on 3 shells. Here's 18 protons pulling on 3 shells. What is happening is the nuclear charge is increasing, and we have another term for that. We call it the effective nuclear charge. You'll learn a little bit more about that in 131. So the effective nuclear charge, that's the science way of saying it, is getting larger as you go across. More protons pulling on that same number of shells, and that is why the atoms are getting smaller. They're contracting due to that attraction between greater numbers of protons in the nucleus for the same number of shells of electrons. Okay, so the going across is the most complex, really, in terms of understanding why a trend is the way it is. Going down the columns, pretty easy to understand. You're adding shells upon shells upon shells upon shells. So first, 1 shell in the first row, 2 shells, 3 shells, 4 shells, 5 shells, 6 shells, and so on. So the atoms in any given family are getting larger as you go down. Size is going to affect bonding. It is going to affect physical properties like melting point and boiling point, and so on. So it's a very important trend. All right, let's go back to the notes. All right, and talk about our next trend, which is connected to size. Our next trend is going to be, in what I've just talked about in the video, is explained right here in this paragraph. The next trend that we're going to talk about is ionization energy. Ionization energy, as it's defined right here at the top of the screen, is the energy needed to be supplied in order for an atom to lose an electron. So you're trying to take out a valence electron, the ones on the outside. The less attraction the nucleus has for its valence electron, the easier it is to lose one. So here is the way, I'm going to do a screenshot here. Here is the way that periodic trends are generally shown. Not so easy for students to understand. So let me bring it into where I can write on it and talk about it. All right, to make it a little easier for you to understand. All right, so usually this is the way it's done. This video today, this lecture is called Periodic Trends. So you see this periodic pattern repeating itself, okay? So this is n equals 1. This is the first row of the periodic table. This is the second row of the periodic table, and this is the third row of the periodic table. You see that this is atomic number down here, and this is energy on the y-axis. So hydrogen is at the bottom, helium is at the top. What is happening as I go from hydrogen on this side of the periodic table to helium on this side? Much larger ionization energy for helium. Couple of reasons why. One, it's opposite of size. As atoms are getting smaller, ionization energy is going to get larger because it is easier. You have less attraction for the nucleus, for its valence electrons. Makes it harder to, makes it easier to take an electron away. So the smaller you are, the less buried your nucleus is. The effective nuclear charge is larger, therefore, and it's harder to take an electron away. So that is why in any given row of the periodic table, the elements that are at the left-hand side of the periodic table, like lithium here in the second row, and then at the end of the second row we have neon, and neon will be up here at the top. Now, there are 2 bumps I'd like to talk about. Okay, it's not a smooth trend. You've got a little bump here between elements 4 and 5. Okay, let's talk about that. Element number 4 is beryllium. Beryllium has a 2s2 valence shell configuration. All right. The next element, number 5, is boron. boron has a 2s2 2p1 valence shell configuration. So what this bump is showing us is that it's harder to take the electron away from beryllium, even though it's a slightly larger atom than boron is, than it is to take it from boron. And the reason why is because this orbital is full, okay, which lowers the energy for beryllium, and it's easier to take one electron out of a p than it is to take it out of a full a full 2s orbital. Okay, so you get a little dip there. Then it starts to increase. Atoms are getting smaller. That's why. Second bump comes between elements 7 and 8. Element 7 is nitrogen. Nitrogen has a 2s2 2p3, 5 valence electrons, one in each box in the p, in each orbital in the p. Okay. And then oxygen, the next element, all right, is 2s2 2p4. So I'm going to put down the p orbital diagram for these two elements. So what it's showing here is that it's harder to take it out of nitrogen than it is to take it out of oxygen. And it should be the other way, because oxygen is slightly smaller. So this is the reason why. Because, and it kind of doesn't follow with this other bump, because you would think that it'd be easier to take it out of nitrogen because you got singles, okay? It's easier to take it out of oxygens because you've got more electron-electron repulsion in that full p orbital than you do here in the half-filled p orbital. So know that there are two bumps there. It's not a smooth trend. You see the same thing occurring for the same types of elements in the third row. It's a detail, but it's an important detail in a way. So ionization energy, opposite of size. So what we're seeing as atoms get bigger, first row, second row, third row, is that gradually those ionization energies are decreasing because the atoms are getting larger. All right, so your third row elements have lower ionization energies and so on. You'll learn a little bit more about ionization energy and trends, how it's related to electron configuration when you go to 131. All right, next we have in our third trend, same trend as ionization energy, and that is that of electronegativity. And the reason that it's important here is because we're going to be talking about this as it pertains to bonding. This property is going to allow us to predict the type of bond. So as soon as I finish talking about these trends, that's what we're going to be talking about. How do I know the type of bond that's going to form between two atoms? And why does it form? Electronegativity is the attraction of bonding electrons to an atom. It is essentially the effectiveness of the nucleus of one atom attracting the electrons of another. So I'd already mentioned that this whole nuclear attraction for electrons not only happens within the atom, but it happens in neighboring atoms as well. I call it the electron hogginess. Now what I've captured here is yet another different type of picture for a trend. I tried to cover some different types of representations of trends, and what I need to do is capture this so that I can write on it. This trend again is exactly the same as it is for ionization energy. Your highest electronegativities are up here in the upper right where your smallest atoms are, so again it's opposite of size, and your lowest is down here at the bottom, opposite of size. Smallest atoms, largest atoms. Okay? So, if I am one atom attracting the electrons of a neighboring atom, the larger I am, the lower my effective nuclear charge is. That nucleus is buried. Nucleus is, buried is the everyday word. Shielded is the science word. Nucleus is more shielded in a large atom, so this nucleus right here is not going to be able to attract the electrons of a neighboring atom as effectively as this nucleus is going to be able to do. Right? Another reason why is the smaller you are, the closer you can get to one another, making this attraction more likely than it is when you're larger. Electrostatic attractions between opposite charges, and that's what's going on here. Nuclei are positive, electrons are negative. Electrostatic attractions decrease, look it up in a physics book, but they decrease rapidly with distance. In fact, it's a 1 over squared thing. Decrease rapidly with distance. So the larger the distance, it's on the new denominator in the equation for electrostatic attraction, and it's a squared term. So it drops off very, very rapidly the farther apart you get the two opposite charges. Okay? So electronegativity is the attraction of one atom's nucleus for another atom's electrons. And electronegativity is going to govern what kind of bonding we're going to have. Okay? How hoggy are you? And there are values associated with electronegativity. You will be given an electronegativity chart to be able to make predictions about bonding type. Right? So going back to our notes, back to the periodic table. So now we're going to talk about types of bonds. And it is going to be completely predictable by two ways. One is the electronegativity difference. That is going to be a numeric way of predicting. But another way of predicting is where the elements come from on the periodic table. So if you are nonmetals and you are bonding with other nonmetals, you are going to form a covalent bond. All right? Nonmetal, nonmetal. Ionic bonds, however, form between two elements from opposite sides, so it is going to be metal and nonmetal. For some reason, students find this concept of distinguishing between where elements are on the periodic table and the type of bonding they're going to form. Of course, it's a completely new idea for you if you've never had chemistry. Very abstract. But we're going to distinguish between these two types of bonding based on one, where the elements come from on the periodic table, but your more rock solid way is going to be this electronegativity difference. Okay? The two types of bonds are very different. You're going to get different properties. Ionic compounds contain ions, real charges. Covalent compounds contain either no charge or partial charges, and therefore their properties are completely different. In order to illustrate this, I've got a little bonding simulation here that I think is very helpful. So you can, of course, go to this on your own. It's bookmarked in the notes. But this is a dog bone analogy for bonding. And I love crazy little analogies to make science things more understandable. And so what we have and we're going to talk about the different types of bonds. We're going to talk about metallic bonding only here. Because, oops, I didn't mean to do that. Hold on, get back to where I was. There we go. Because we're not really going to spend a lot of time on metallic bonding. It's a different type, and we're going to cover it right here with the dogs. All right, so ionic bonds, opposite sides of the periodic table. So you're going to have, if we watch this simulation one more time, you've got a large dog and a small dog. Now, this large and small pertains to you can think of it as pertaining to electronegativity. Chlorine is a nonmetal. It's on the left-hand or right-hand side of the periodic table where there are high electronegativities. Sodium, metal, coming from the left side of the periodic table, so low electronegativities. So the size of the dogs really has to do with electronegativity here, because in fact, the size in terms of the atoms would not be the way it's depicted here. The metal would be larger than the nonmetal. But anyway, so the chlorine has a high electronegativity, a much higher one than sodium does. All right, so we can assume that we can predict that sodium and chlorine will form an ionic bond based on the fact that they are from opposite sides of the periodic table. So remember I said we're going to be able to do this based on where they are on the periodic table, but the other way that we're going to be able to do it is by electronegativity difference. All right, so let me make a screenshot here so I can do some writing, and I want you to get your electronegativity charts you were given. In front of you so that we can look at electronegativity differences for these elements in these bonds. Not able to take a screenshot in while I'm on the internet, so we'll just talk about it here. All right, so sodium and chlorine, electronegativity charts in front of you. Chlorine has a 3.0 and sodium has a 0.9 electronegativity difference. I'm sorry, electronegativity. We are going to take the difference between these, which would be 2.1. In just a moment, I'm going to give you, and I believe it's in the notes already, but I'm going to give you some cutoffs. Now, talking about electronegativity differences in terms of predicting the type of bonding, all right? There is not ionic bond, line drawn in the sand, then we have covalent bonds, and so on. It's not like that. You start off with electronegativity differences of 0 on the left, all right? And then you go to the right and then you increase your electronegativity difference. As you move to the right, where the electronegativity difference is getting larger and larger, and I will draw this out in a moment, you are getting more and more ionic-like. We say that the bonds have more ionic character. Okay? What I'm going to tell you is that if we are between 0 and 0.4, we are going to have this type of bond right here. Covalent bonding, where you're sharing electrons, okay, not one highly electronegative element like chlorine taking an electron away from sodium, and you ending up with a positive and negative charge as what happens in ionic bonds. In covalent bonding, you share electrons. If the two elements are exactly the same like they are in Cl-Cl, then your electronegativity difference is 0. And so then you have a pure covalent bond, like here in the middle. If you have an electronegativity difference like the third picture here, let's look at what it is for hydrogen and fluorine. Electronegativity difference between hydrogen and fluorine is 1.9. 4 minus 2.1. Subtracting. That bond has a lot of ionic character. That's how we would say it. In fact, fluorine with the higher electronegativity right here is attracting those negative electrons closer to himself, or to itself if it's an atom, and therefore it's taking on the charge of an electron because it's attracting something negative. Hydrogen, in this example, is taking on a slight positive charge. So when I said that it's becoming ionic-like, we actually see that in the properties for these types of covalently bonded substances. Okay, so you start off on the left with 0, pure covalent bonding, and as you get closer and closer to 2, an electronegativity difference of 2 is going to be our quote-unquote cutoff for an ionic bond versus a covalent bond. All right, before we leave this website, let's talk about metallic bonds just once, okay, in the course. Bonds between metals. The communist view of bonding. What happens when metals like copper metal or sodium metal or iron or any metal like that, when the atoms are bonded together, as they have to be, in a sheet of aluminum or a copper wire, and the fact that we're able to take those substances and hammer them into sheets and make wires out of them is because of this type of bonding. This type of bonding is that the valence electrons, the bones here in this bottom picture, are shared equally by all of the cations. So you take the valence electrons away from, the valence electrons from each of these atoms. They are then shared in a sea of electrons. That's how we describe it. The electrons are mobile. All right, very important. And so it's a very strong type of bonding, but it enables, because of the mobility of those electrons, it enables you to have the properties of ductility, which is being able to pull something into wires or malleability, which is the enables you to take a substance and hammer it into thin sheets. It's because these electrons are moving, and that then the atoms can slide past one another and so on. It also enables metals to conduct electricity, unlike other substances, covalently bonded substances and ionic substances, when they're in their solid form. If I take this net positive and negative cation and an anion, and I put it in water, it will conduct electricity. Or if I melt it, then these charges are mobile. Okay, in a melted substance, a liquid, things are moving, then it will conduct electricity. But when it's in the solid form, it cannot. You have to have moving charges to conduct electricity. So ionic substances can do it when melted or dissolved in water, and metals can do it in any shape they're in solid, liquid, or liquid form, and they have amazing properties because of this difference in bonding. Very, very different kind of bonding. All right, back to the notes, and let's go to notebook and talk a little bit about that scale that I was mentioning. All right, so I'm going to get a blank spot here, and we're going to talk about electronegativity difference. Okay, so electronegativity difference. If I have a difference, so if I have ClCl, Cl2, that was the example on the little simulation. The electronegativity difference here is 0. This is a pure covalent bond. We also have another word for that, and we call it nonpolar. All right. If I go between 0, and I'm just going to draw an arrow as we go across, and I'm going to put increasingly ionic. When I get to, now different books will give you different cutoffs, and these cutoffs are just for students to enable you to make a call, really, is what it is. If I get to 2, anything past 2, electronegativity difference of 2 is ionic. Pretty much anything from 0 to 2 is covalent. But as we get closer to 2, we're getting increasingly ionic-like. The cutoff I'm going to give you is between 0 and 0.4 for a pure covalent non-polar bond. 0.5 to 2 is going to be a polar covalent, where I have some charges, like the HCl example HF example in the simulation with the dogs. And if I am greater than 2, like sodium chloride, metal, nonmetal, I am going to be ionic. Now, there are not metal-nonmetal combinations that are not ionic by electronegativity difference. They have some covalent character. And anything that's covalent is going to be nonmetal, nonmetal. Okay, so those are going to be our way of taking electronegativity and subtracting to get to make a judgment call about what type of bonding you have. So electronegativity is really important in terms of being able to predict. All right, so we're going to move into ionic bonding and predicting formulas and so on. The thinking that we need to use, we started at the end of lecture 6, and we're going to review that one more time here in this practice. So let me give us a little more room, take a screenshot, and then we will. All right, so the first thing we're going to do is we're going to get our periodic tables in front of us so that we can arrange these elements here in order of increasing ionization energy. Now, these ACT type questions, I have been in the past as a student notorious for doing backwards. So let me tell you how I've conquered that. I have conquered it by finding my extremes. So what is my highest? What is my lowest? Put them in the right place, and then I generally don't screw it up. All right. So I'm looking at gallium. Find gallium. It's on the third column 3A. Indium right underneath. Okay. Fluorine up there at the upper right-hand corner. Silicon group 4, and nitrogen, group 5. So what out of these 5 elements, which one has the highest ionization energy? It is the one closest to the upper right-hand corner, and that would be fluorine. Now this says increasing ionization energy, so that means fluorine has to be on the right. So that is my anchor on the right. Now, which of these elements is farthest to the left and down? That would be indium. Okay, it's farthest to the left and it's the one furthest down. So that is going to be my anchor on the left. If this were in order of decreasing, which is number 3 is asking me for, then I would flip it. Highest on the left, lowest on the right. All right, so we'll come back to that in a moment. Now, working from either end, start putting in the rest of the elements. So I'm taking care of indium. What comes out, what is closest to fluorine? That would be nitrogen. Now you can put commas in here, or you can put greater than or less than signs, but they need to be going in the right direction. So fluorine is going to be larger than anything, so if I'm using a greater than sign, it would go that way. It is larger than nitrogen. Okay, so we've taken care of nitrogen. What is next in closest to nitrogen? Is it silicon or is it gallium? It would be silicon because it is on the next row, and it is, so gallium's farther to the left than silicon. So silicon should be here, and then gallium would be here. So it would be like that. Or you could write it as indium, comma, gallium, silicon, and so on. I think you need to get good at doing it both ways. Okay. So if I come down here to number 3, where I flipped it, then it would be fluorine is greater than nitrogen, which is greater than silicon, which is greater than gallium, which is greater than indium. So we've done 1 and 3. Number 2 is about size. All right, increasing atomic size. So I want my largest atom to be here, and I want my smallest atom to be on the left. So putting in those extremes so you don't get it backwards. So which element out of this group, find all of them on the periodic table, is your largest, your atom closest to the lower left? And that's going to be your largest. That would be cesium. Okay? If it feels like I'm going too fast when I ask a question that way, just stop the video and find it in your own time. All right, so we've taken care of cesium. Which of these atoms is going to be farthest to the closest to the upper right-hand corner? It's going to be, find the rest of them. Cesium was easy. Pb and sulfur. Sulfur is the farthest to the right and highest up. So my smallest atom out of this group should be sulfur. All right, so what's closest to sulfur out of this group? Selenium is right underneath. So sulfur is smaller than selenium. Okay. What is now next to selenium? That should be antimony. And then lead would be next. All right. So find your extremes so you don't get it backwards. Take it from someone who's done it backwards many, many times. All right. Scroll this a little bit. Oops. There we go. Oops. Okay. Number 4 is a repeat of what we've done in lecture 6, and it is absolutely essential to what we're going to be working on in lecture 8. So this thinking of metal or nonmetal, how many valence electrons does it have, and what ion is it going to form, is the first thinking that you have to do in putting compounds together, because you're going to gain and lose if you're talking ionic. One dog is going to take the electrons from another dog. The atom with the highest electronegativity is going to take electrons and become negative, and the larger atom, the metal, is going to become positive. So sulfur, non-metal, 6 valence electrons. Number of protons we can go ahead and fill in. Let's do that first. 16 for sulfur, scandium, 21. So this whole idea of where do the charges come from, I think this is the last time we're going to do it. All right, but it's something that I added to the notes after I taught the course once or twice because I realized that students just weren't understanding where the charges came from. Okay, so there are my atomic numbers, don't change. Electrons do change, gains and lose, depending on where you are on the periodic table. So we've already said that sulfur is a nonmetal, 6 valence electrons, so therefore it gains 2 to make 8. Nonmetals gain to make 8. They take what they have and they gain to make 8. So it gained 2, so the number of electrons is not 16 as it was in the atom, it is 18 in the sulfide ion. We change the ending of the nonmetal to an IDE. There aren't that many of them. We leave the metals alone. Okay, so a little naming. All right, scandium, the element, we've already said here that it's 3+, but let's reason through why that is. It is a metal. It has 3 valence electrons. This is one of the transition metals that's predictable. Silver is the other. And the last one is zinc. So these 3 I can predict from the periodic table. The others, as you'll learn in lecture 8 from the transition metals, we're going to treat differently. All right, so we know that scandium is going to lose its 3 as we would predict. So instead of 21, it has 18. Chlorine, nonmetal, has 7 valence electrons. If this thinking of calling out the element, whether it's a metal or nonmetal, and how many valence electrons, you haven't conquered that yet, you need to go back to lecture 6. All right. Chlorine, nonmetal, 7 valence electrons, so therefore it gains 1 to make 8. And we don't usually put the 1 here. And it has 18 electrons instead of the 17 that it started off with. All right. Silver, metal, has 1 valence electron. It's a metal, has 1 valence electron, so it loses that 1 to form a +1 ion. So instead of 47, it has 46. Okay. Phosphorus, nonmetal, has 5 valence electrons, therefore it gains 3 to make 8. And instead of 15, it now has 18. So you see some similarities here for many of these ions. They are isoelectronic in that they have the same number of electrons. We have very different charges. They are all becoming like, what's the element on the periodic table that has 18 electrons? Like argon. Now this idea that everyone wants to be like a noble gas is a very simplified one, and if your high school teacher essentially taught bonding from that perspective, it's a good place to start. But as you'll see when we get into just pretty quickly here in ionic bonding, that the majority of the elements on the periodic table don't do that. Now nonmetals, yes. Nonmetals gain to make 8. So they are mimicking noble gases, because noble gases have 8 valence electrons. Metals, however, there are some metals, electrons. There are some metals that lose their valence electrons, thereby becoming like noble gases. However, here's the metal. Silver is a metal, and doesn't have 46 is not a noble gas. All right. And many metals, majority of the elements on the periodic table are metals, and the majority of them do not lose electrons, so they become like a noble gas. All right, so just plugging that idea in right now. All right, so we finished that. And if you want a different source for information about chemical bonds, here's another video for your here what I've just said. And then I'm given an example where, yes, it's true. In sodium and chlorine, sodium loses an electron because it's a metal, has a low electronegativity. That's why it forms a positive ion, which we've already identified in a previous lecture as we call those cations. Chlorine, nonmetal, gains to make 8, gains 1 to make a -1 charge. Negatively charged ions are called anions. And both sodium and chlorine here are mimicking a noble gas by gaining and losing. Now, the nature of the bond they're forming is the attraction between those positive and negative ions. That's all an ionic bond is. Many students come to chemistry from biology, or they're taking biology at the same time. Ionic bonding is really not a biological, I don't want to say it's not a biological phenomenon, because there's a lot of ionic substances in our bodies. We absolutely have to have ions for transport across cell membranes and so on and so forth. But you do a lot of pictures of molecules that are mainly nonmetals, and therefore they're sharing electrons. Okay, ionic bonds, positive, negative, strong attraction, no sharing. We don't do dashes. We don't do Lewis type structures for them. Some people do. I think it's kind of silly. Couple things that are very important, and let me go ahead and talk about those, is the ratio between ions. Understanding exactly what this formula means is important. I used to make my high school students draw particle pictures at this point to emphasize the fact that for every one sodium, there is a chlorine. So it's a 1-to-1 arrangement. When this compound breaks apart, and we'll be doing that after we talk about bonding, we'll be taking these substances, we'll be putting them in water. You will see that in a simulation in Lecture 8. For every time we put one of these formula units in water, we generate 2 ions. 1 sodium, 1 chlorine. When I put this substance in water, which is not very soluble, meaning it does not dissolve very well, it is 1 magnesium to 1 oxygen. Again, a ratio of 1-to-1. When I put calcium and chlorine in water and dissolve it, I get 3 ions. It's a 1-to-2 ratio. So I get 3 species. Same thing is true for this substance. So let's talk a little bit more about the naming, and then I'm going to end here, because that's this is where Lecture 8 picks up. All right, so naming, picture of ionic compounds. They're all solids, alternating positives and negatives. So before I leave here, why are the metals smaller than the nonmetals? Because the metals are losers, so they get smaller, and the nonmetals are gainers, like what happens when we lose and gain weight. All right, let's go back up and just talk about those names and end this lecture. So I said already that we change the ending of the nonmetal and leave the metal alone. When I write the formulas, the metal comes first, the nonmetal comes second. Do not change the name of the metal. So this substance here is called magnesium oxide, calcium chloride, potassium oxide. Like I said before, there aren't too many nonmetals, so you will get used to changing those endings. And to end this lecture, what I'm going to do is write down the different nonmetals and their endings to help you out. How about that? So if I look at my periodic table, now carbon is a nonmetal, but it generally does not form ions. But if it did, it would be carbide. I'll put just not common. Carbon loves to share, does not form ions very much. Nitrogen, all the nonmetals like to share. They share to make covalent compounds, just the nonmetals together. So, but when they are combined with the metal, and you actually, even in covalent compounds, the second element in the formula is you change the ending the same way. So we're learning something we're going to need for covalent bonding as well. Nitrogen becomes nitride, phosphorus becomes phosphide, arsenic becomes arsenide, oxygen becomes oxide, sulfur becomes sulfide, selenium becomes selenide. It does come up every once in a while. Elements below those on the periodic table generally are metals, so we're not going to change the names of those. Fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide. And becomes iodide. So you really, it's not very many. And the noble gases generally don't form compounds at all, much less ionic ones or compounds at all. So nonmetal endings for the few nonmetals that are on the periodic table. And that is going to end lecture 7.